Welcome, everyone. Thank you for joining us for this school, summer school, or series of lectures on techniques in active tectonic study. So my name is Ramon Aerosmith, and I'm from Arizona State University. I'll introduce myself some more later. So I wanted to just start with some thank yous to people who have really helped to get this going. So starting with Gayatri Mariani, so she's a PhD student working with me at ASU, and she's also the course assistant. And so if you have questions, you can also ask her. We'll be working together. And then I want to thank Mudrik very much for doing everything to get things going and help design the course and coordinate things. And then the senior colleagues here at LIPI and ITB, so Irwan Milano, Yanni Hillman, and Ecoli Yulianto. And then most important is to participants. Thanks for being here. So this first lecture is an introduction. So I'm going to kind of do some definitions, and then we have many lectures, so we'll go into lots of detail over the next 2 weeks. So the first, just in words, what we're trying to do is study the problem is that active tectonic processes are those that occur over time scales of interest to society. This is one reason why we do this work. And the study of these processes builds on fundamental knowledge of the underlying phenomena, so how the Earth works. And it also can be applied to anticipate hazards. So there's two things we're always doing. One is improving our knowledge of how the Earth works. And the second one is doing something useful with it. So the tools that we use generally have to characterize the elements of the system of processes at the appropriate time and spatial scales. In spite of the fact that we know as geologists the record is incomplete. Things are disappearing or they're under lots of vegetation. So it's a hard problem. But I hope the tools that we'll discuss over this time will help everyone to do a better job. And then the final results are to increase our knowledge of the underlying processes and help to fill your toolbox so you have different tools you can use. Because one point is that no one tool or data set is sufficient for the integrated understanding. We have to use many tools to get the best answers we can. So my request and my excuse to you is please ask questions and make contributions, because I'm here, came all the way here. I want to help. I want this to be interactive as possible and useful. So we have a schedule, but if you have some special requests, we can do it. We have time. And then you can also teach me, because I'm not so experienced working in Indonesia. We have some projects we're getting going here. So many examples I will have are from other places in the world, but hopefully you'll see how some of the ideas may apply here, or you may say, oh yeah, here's a really good example from my experience. So let's go both ways, okay? So here's then just the outline of the rest of the lecture. We'll do our introductions. I'll overview the schedule. Then I'll have some general motivations for why do we do earthquake hazard studies, and then show, as we all know, that the real hazard is to growing population and infrastructure around the world. A quick reminder of magnitude and intensity, and then show for seismic hazard assessment how the active tectonic study applies, especially to the initial parts of seismic hazard assessment. So here's just a quick introduction of what I was doing, where I came from. So here's, you can see, this is, there's my office is in this building here in Arizona, in the United States, also Gayatri, so Arizona State University from above. Our university is a big one. There are 70,000 students that go to our university. So then we fly out. This is Phoenix. So Phoenix is in the southwestern United States, and it's in an old part of the basin range, so an extensional zone, but the faults are no longer active. But we still see basins and mountains. However, as we zoom out, we see California is on the left and the Pacific Ocean, and that's the plate boundary that we live on. And so you can see a real change in the topography, but you can also see these red arrows are the GPS velocity vectors for the Plate Boundary Observatory, which is a major infrastructure activity by the United States academic community. And you see this arrow is 32 millimeters minus to the east, so it's moving west, and also 35 to the north. So these are relative to stable North America. So this region is moving northwest at about 35 millimeters per year, and that's the San Andreas Fault Zone. So this is where many examples that I will present come from, but it's part of an integrated system around the Pacific Ocean. So the San Andreas Fault is a transform boundary. It connects to a little subduction system here in the Pacific Northwest, another transform, the Queen Charlotte Fault, and then the big subduction zones of the North Pacific, so Aleutians, Kamchatka, going around to Japan. And then we see that this system connects to where we are. So the Sindus system is one that you all are very familiar with, very complex tectonic environment, really amazing laboratory for studying active tectonics. Also, many people live here, so it's important inspiration for us to do our work. And so in here you can see, and we'll discuss in the second lecture today, a little bit of a review of the tectonics of Indonesia. And one thing you can see here is there's no coordinated GPS velocity vectors that I can show, although there are GPS observations being made in the region. We don't yet have the regional geodetic network that is communicating in real time. So this can be an example of an aspiration for the future for the region. Moving on. So this is just my web page, just introducing myself. So this little flag here in the lower left is the flag of the state in the United States, New Mexico, where I came from. So the region, again, near to Arizona, southwestern United States. And then my PhD was in Stanford University. So this is S and the tree of Stanford. And so now I've been at this Arizona State University for 18 years. And my research is on active tectonics, but that means lots of geomorphology and also lots of structural geology. And I also teach many relevant classes, geologic disaster, structural geology, geomorphology, computer geology, field geology of various sorts, and advanced structural geology, tectonic geomorphology. So one of the things that I will present to you is a lot of content from these classes. So that's, we have so much to talk about. I'm pulling everything I can from my classes. So hopefully it's at the right level. I know you are all advanced students, so you have to tell me, okay, go slower, go faster, okay? So here's just some places I've been working. And so over these 20 years, I've been able to look at different examples of active tectonics from different tectonic regimes. So you saw at the beginning my example of San Andreas Fault. This is where most of my work has been. But also rift systems, Baja California, East Africa, and then collisional systems, the Andean back arc, and the India-Eurasia collision system. And I have done also a lot of work in Central Asia, so Pamir Mountains and Altan Fault system. And now here working with Gayatri and colleagues in Java. So just one example of the kind of research that is really interesting to me and is an example of active tectonic studies is looking at the deformation over different time scales. And so you can see on the upper right is the GPS velocities in Southern California, as I showed before. And you see they get longer as you go across the plate boundary. But that's just 10 years of data. But then we come down here, and this is the geomorphic record of the deformation. And this is 135 meters of offset along the San Andreas Fault in 3,700 years. So this is a famous study from Kerry C. Many of you know from his PhD. This place is called Wallace Creek. So, how do we compare the deformation over what you might say this decadal time scale or geodetic time scale with deformation over the geomorphic or almost geologic time scale? And in between, that deformation is accommodated by earthquakes. And so how can we, it's like a movie, right? You play each frame at a time, one at a time, and each frame, maybe an earthquake slip event, and that accumulates over time. So here's an example where we think that the last earthquake may have offset between 5 and 9 meters at this location, but it's repeated many times, and it's been very well localized just right along this line. So it's a plate boundary fault. And this balance is one thing that interests me a lot. And so we'll come back to this, but any questions so far? Okay, so later you have to ask some questions. So then just to introduce Gayatri, so do you want to speak or shall I? Okay, so I'm very fortunate that Gayatri came to work with me. She originally did her undergraduate degree at Gajah Mada University in Yogyakarta, and then she went for her master's at San Diego State University, and she worked with very famous paleoseismologist named Tom Rockwell there, and she did a quite interesting study on the San Jacinto fault, looking at the evolution of a extensional stepover. And so later on, she'll show us some of the methods that she used to examine this place. And then after her master's, she came to work with me, and so the main project that we've selected to work on is working on the neotectonics of Java. And so this is a challenging one because it's in this situation where the subduction is basically perpendicular to the arc here. And so most of the deformation is along the subduction interface, and there's not a lot of upper plate deformation, but there is some, as you know, how the landscape has developed, and then also important earthquakes. For example, the Yogyakarta earthquake from 2006 was very dangerous, even though it was a relatively small event. So this is Gayatri. And so one thing she's doing is, in terms of assisting us for the classes, she's putting all this content on our website. So this is the place you can go. So right now, for convenience, we're sending it across the Pacific, but later on, we can try to move it here, but it's easy for us to control our site. So, but this is where you can go to find this information and other links, and all the talks will be there, and we'll try to video the talks. So we'll see how it goes. Okay. So moving on. So then the outline of the lectures and the demo and practicum is that the idea we had with Gayatri at Mudrik was to do 3 lectures in the morning each time that are more general. Maybe other people can come. And each one's about like each hour. So we try to go, start at 9, start at 10, start at 11. Hopefully I don't talk the whole hour so we can get a short break. Then we take a lunch break. And then in the afternoon is more of the practical activity demonstrations, and we'll go to the computer laboratory upstairs. And so people should come, and it's a chance to work together, have some exercises, and we can also discuss some of your research. And so then if you want to get a certificate for this class, then you want to come at least 75% of the time, okay, just to show that you have truly participated. So it's about 8 of the 11 days, okay? So big job, but hopefully something good for you. Okay, so it's a little bit small print, but this is the schedule as we have it now. And we may change it a little bit because we are discussing how we want to do a field trip. But today is Thursday, so we have these 3 lectures today, introductory lectures on plate tectonics, structural geology, geometry of active faults. Then this afternoon we'll do simple dislocation studies. So how you can simply compute the effects of earthquakes on the ground surface both at the fault and beyond. And so it's a good tool to get us discussing about changes in topography. Then tomorrow we'll do some geomorphology and then 2 lectures on earthquake processes. So earthquake magnitude, frequency scaling, and earthquake cycle. And then tomorrow afternoon we continue our demonstration and exercise doing Coulomb. So Coulomb is a fully 3-dimensional dislocation-based software developed by U.S. Geological Survey and also Japanese colleagues. And I'll teach you how to operate it in a basic sense, and then you can use it for your own research. Okay? So then Saturday, we do a tour of deformation at different time scales, geodetic, geomorphic, geologic. So how we measure, how we balance measuring, how the processes over different time scales. And then Saturday afternoon, activity would be mapping and landscape reconstruction. So this is really a GIS activity, but interacting with digital elevation models and some mapping. So then Sunday, no class, quick break. And then in the current schedule, we would go out to Lembang Fault all day on Monday and just discuss some different sites. And some of the things we will have looked at on Saturday in the digital data, we'll go to those places and discuss them. And this area also is the coverage from the LiDAR that was on the intro slide. So we can look a little bit at the high resolution topography that is available. And that's a really powerful tool for active tectonic study. Then we go into methods, so geophysics, trenching, and on Tuesday, then my area of where I've really been working a lot is high resolution topography. This is LiDAR and also structure for motion. So we'll do a big exercise on how this works, what the technology is, how you process the data, and so forth. Then Wednesday is fault zone mapping. So kind of coming back a little bit to Lembang example, but also discussing styles. How do you make active fault map? What are the things we have to discuss and consider? And then tectonic geomorphology, so looking a little bit larger scale, how do the river networks especially respond to active deformation? And this bringing understanding from other places, especially the Himalayas, to here. And then that practical activity would be slope area analysis, so morphometric analysis of longitudinal profiles of rivers and also digital elevation models. So then Thursday next week is on geochronology the whole time. So carbon-14, optically stimulated luminescence, cosmogenic radionuclides, so forth. So be a big day for that. And then in the afternoon, we do some examples of how you take these data from geochronology and integrate them. So build a geochronologic model for a site, like a trench, for example. So then on Friday, some moving more then into archaeoseismology and then really paleoseismology. So, and then just examples. So we will have done all the methods by this time. So then we can do examples and styles of deformation and kinds of projects for extensional settings, volcanic settings. The next day, reverse faulting and strike slip faulting and paleo intensity, so landslides and liquefaction. On Friday, our demo and exercise will be paleoseismic sighting and trench log interpretation. So how do you decide where to dig? And what do you do once you dig? And then on Saturday, we'll do some diffusion modeling and looking at marine terraces. This is an area of expertise for me, for my PhD, the diffusion models. Then on Monday, we'll do subduction zones. And so basically looking at corals and other examples of vertical changes in subduction systems over time, and also looking at tsunamis. And so Echo is here, and also Danny, lots of expertise here, not just me. So maybe we can get some guest lectures this day. And then finally, the last day is some big ideas. So EarthScope, what's EarthScope? It's a big integrated network of observatories in North America that I am helping to be a leader in, and maybe it's an example for the future for you guys. Also then, big ideas, earthquake early warning, networks, earthquake forecasting, open data, and then the last one would be education outreach. How do we share these ideas? And then the last activity would be some presentations from the students. So something you might work on this next 2 weeks or something you already have. So it could be, you don't have to be nervous, but a chance for you to explain what you have done. And we'll organize it so everybody has the right amount of time and proper instructions. So that's the plan. Hopefully it covers some things that might interest you. So if you have other things that you want to say, hey, I thought you were going to cover this, let me know, or let Mudrik or Rupture, because we can change it. So any questions so far? Okay, let's go. So here's some textbooks that we're using. I carried these across the Pacific. Of course, you learn a lot now in these modern days off the web, but there's some really nice textbooks coming out in these areas of active tectonics and paleoseismology. So there's the upper left, it's Bill Bull, Tectonic Geomorphology of Mountains, kind of a classic approach. The Tectonic Geomorphology book, the second one from the left, is really very nice. And if you had to only buy one book, this might be the best. It's the newest one also. Then Mechanics of Earthquakes and Faulting by Schultz. It's a really good one. How do faults work? How do earthquakes work? Not so technical, but lots of geophysical approaches are in there. The other excellent book that maybe would be the second most important one to buy is the McAlpin Paleoseismology book. It's newly updated and it's really a standard. Then a famous one is The Geology of Earthquakes on the left, lower left, Yates, C. and Allen. This one, 97. It's one of the earlier of these books, but it really has a great set of ideas about the situation of earthquakes and how we can study them using geology. Active Faults of the World is a new book from Yates. It's more of just a survey of the whole world, all the active faults in the world, and a really great reference, like an encyclopedia. It's amazing. And then, of course, you have to know some seismology, and that's Shearer and also the Bolt book. Just after all, we're studying mostly paleo earthquakes and their effects. So what are the basic seismological things we need to know? Okay, so this is where also, if you see some figures, a lot of times I'll take them from these books. Okay. So now just a little bit on kind of motivation, to remind us this is very serious business, what we're doing, and the application of the study of active faulting is to, try to help people. And so we see that human fatalities and natural disasters over even just the last 25 years, this is up to 2006, shows a bit of it's sawtooth by year, but you see some increase. And this doesn't have the last few years of earthquakes, including Haiti. So, we know that natural disasters, not just earthquakes, there's also, weather-related phenomena, hurricanes, and also then volcanic eruptions. And especially here in Indonesia, you have big double sets of hazards with significant volcanoes. And there's many, many people who live here. And so this is, really should be an inspiration for us all to do as good of a job as we can. Then the other thing, of course, besides the people, is the economic losses. And Indonesia is a growing, developing country, becoming more important globally, economically, but earthquakes and other natural disasters are expensive. And so we see, for example, it's loss of the infrastructure, but also productivity. People can't work. And this just shows that this is a really big business, this figure here, which shows a number of events over time and economic losses, which are, in billions. So almost $1 trillion was lost in the 1990s due to natural disasters. And in the insured losses, we're not quite so high, but this big business, so these big insurance companies, they care about the knowledge that we produce, because they are trying to best estimate, how to charge people for insurance. So it's an economic significance. And many people, or some people who study active faults, go to work for companies that aid insurance companies or other big financial organizations because they want to, save money. So then other things about these natural disasters that are important is they're big and they go beyond just the ground shaking, let's say, from the earthquake or the water flow of the tsunami. This is a quote from a guy who's a structural engineer, and he went to Haiti, and he said the tragedy of this thing, that was 3 days after the earthquake, the city was littered with bodies, and by God, this was not an earthquake disaster. This was a disaster caused by the construction industry in Haiti. The construction industry that did not know how to use codes. They did not have any codes. The people that built these things, the buildings were in bad shape. These are the people that caused this tragedy and loss of human life. In the past, I've told people we have to design things and construct things and assume that our children, our grandchildren, and our mother are going to be in this building when the earthquake hits. So you have to do a proper design. So it's just, taking responsibility. So this is a little bit more for the engineers, but the information that we produce in active tectonics goes to those guys. And so we want to be as careful as we can. So another thing is changing politics, right? And so, the 2004 earthquake in the Indian Ocean, Boxing Day or Aceh earthquake, it obviously was a great effect on Indonesia, but it also changed the politics of their interaction with the Free Aceh movement, right? And maybe this was it was partially because of the direct effects of the earthquake and the tsunami, but also it was the changing kind of external input, the foreign aid coming in, maybe changed the relationship, right, between the government and the other group. So, these are why the earthquakes are so important, because they can change the world, beyond just what happens to people. And then another example, the third one, and then I'll move on, is, for example, nuclear power. So, in the Japan earthquake, the tsunami affected the Fukushima Daiichi earthquake, or nuclear power plant, and this was unexpected, right? Because the ground shaking at the power plant was not so strong that it affected things in any significantly negative way, but the tsunami was larger than the walls that were built for the expected tsunami, and so it caused a big problem. And it also, the Japanese people became skeptical then of nuclear power and also their government, right? And so you can see these polls here. This is right after the earthquake and then 1 year later, and it's getting worse and worse in these years. So the Japanese, they said, should nuclear power be reduced? And there was big change going down, reduce it. And then also they really disapproved of their government. And so the reason why this is important is that the global energy trade drives geopolitics, right? So now Japan can buy lots of gas from some other places. So, and it goes beyond Japan, so global attitudes towards nuclear power have changed. So just examples of how earthquakes affect us. So here's the other thing we always have to keep in mind is that the top chart shows the magnitude of earthquakes over the 20th century. And you see, because some people say, are earthquakes getting bigger? And the answer is, well, no, not really. Look at what happened in the 1950s and 60s, were the biggest ones in the 20th century. Now, it was quiet in the 80s and 90s. And then we got another burst of big ones here at the kind of beginning of the 21st century. But really what we know for sure is changing is human population growth, right? So during this time, the population has almost has doubled. And so this is our job going forward, right, is to take care of this. So another thing, and this kind of goes with what I was saying about to the first order, the magnitude of the earthquake seems to go with the losses. So this is work that's been done by Roger Billum at the University of Colorado, and he's really started to look at the data associated with big earthquakes and effects on people. And so what he could summarize was that, for example, the Sumatra 2004 earthquake was really bad because it was big and many people were lost. But and this is a log scale on the left, we see, for example, Japan was almost as big in terms of magnitude, but maybe an order of magnitude fewer people lost. Chile earthquake was really also quite big, but many fewer, another like 2 orders of magnitude fewer than the Sumatra earthquake, mostly because there weren't so many people there, but also the Chilean coast has been hit by a number of recent large tsunamis, and so there's a good memory of what happened and also good anticipation. And then the other unfortunate example is Haiti, which was actually a smaller earthquake, only magnitude 7, but the losses were great. And that's the problem with Haiti was that, and Eduardo Fierro said it, is the construction was not good. And it was okay because the hurricanes come every 5 years. We have heavy concrete buildings, good for wind. But if you have an earthquake every 100 years, unfortunately it happens in our time now, and those buildings couldn't handle it. So multi-hazard trade-offs is another key issue we have to deal with. So then just going around the Pacific Rim, we see these great earthquakes, and this last 50 years, it doesn't show, this is a little bit older, so it doesn't show Haiti or Christchurch, which are other important examples of earthquakes in this time. So just kind of a few more points, these motivating points is another figure from Billum, where he's showing super cities and plate boundary strains. So super cities are more than a few million people, and then the color shows the strain rate. And so what you can see is there are some big cities that are in continental interiors, so maybe they have a lower earthquake hazard, but there are many big cities like these ones here in Indonesia or China, all along this sort of Eurasian, the southern part of Eurasia collision system where they live near to high strain rate zones, right? So examples are Istanbul, Tehran, many cities of Southeast Asia. So we have to be careful to keep in mind these things. So any questions so far? So that was kind of a pass through like big picture. Why do we care? Why is this important? More additions, comments? Okay, so now let's just remind ourselves a little bit about intensity and magnitude. And so what's intensity of an earthquake? It's what you feel, right? And it depends where you are relative to the earthquake. How does that compare with magnitude of an earthquake? Yeah, so it's constant. It's a number, and it doesn't change with space. So it's always important we always keep these in mind. We usually care about the magnitude of earthquake, but sometimes the secondary effects are driven by intensity variation. So, landsliding, liquefaction. So this just shows, this is in the U.S., the United States Geological Survey has a web-based system. It works globally, but they have it working in the United States, where if you feel an earthquake, you go to the website and you type in your zip code. So it's kind of a generalization of your address. And then you fill out some information. What did you observe over the effects on the people and the structures around you? And then it accumulates this information. And so this is 500,000 reports of earthquakes from 1999 to 2004. So just 5 years. This is what people were feeling. And so you can see, near the plate boundary, there was a big earthquake here, 1999. That was called Hector Mine. Another earthquake here, Parkville, 2 of them. So these are obvious. But there are some earthquakes in the continental interior that people feel as well. And sometimes the seismic networks aren't dense enough to notice them, but it's more the people say, hey, I feel something, you know, and one person, they might be kind of crazy or confused, but if many people feel it, it's probably with a small earthquake. So then we compare that with a seismic hazard map, and you can see that the U.S. seismic hazard map generally anticipates these places where people are feeling earthquakes. But there are some, you know, like this place here is called Central Virginia Seismic Belt, and there was an earthquake there last year that affected Washington, D.C., so the government, you know, felt this earthquake. And you can see in this diagram it's not such a high hazard zone, so it shows a challenge we have for earthquake forecasting. And so this just shows a summary of different magnitude earthquakes, but all plotted at the same scale and same color, same spatial scale, and same color for intensity. And so you can see, for example, this magnitude 8.8, this Chilean earthquake, was quite large along the coast, and this is just the yellow part, so the strongly felt. Whereas if you look at the Haiti earthquake, the distance of the yellow zone of higher intensity is pretty small. Same with this El Mayor Cucupa earthquake and the 7.3, the main shock of the Christchurch sequence is, you know, quite a bit smaller. And then these magnitude 3s and 4s, you don't see even any of the yellow shaking. So this sort of fundamental issue of basically, you know, intensity is the shaking in an earthquake at a point. It can vary with position and also with substrate if you're on hard rock or in a basin. But the magnitude is the measure of energy released in the earthquake, and basically that energy scales with the size of the fault, right? So this is important. We have to keep that in mind. Okay, so now moving into seismic hazard assessment. So this is what we might do if we're studying active tectonics. Where does our information go? So there's 4 steps that are the classical definition. And well, first we used our understanding of what's happened in the past and also how we think earth faults work to forecast future seismic shaking and secondary effects. So the geology is especially involved in the first 2. So we need to find the faults, the active faults. So this is our job when we're doing active tectonic studies, when the information we use for seismic hazard. And we need to know where they are and their extent. And sometimes we don't know where they are, but there's some kind of area sources. We don't know exactly where it is, but it's going to be some size event. And then that obviously will affect some site. So first point is identification of sources. The second one is coming up with the recurrence model. So what are the sizes and how often do earthquakes occur along these sources? So this is the main job for the active tectonics people and geologists. Also other data goes in. The ground motions then, once we know the recurrence relationships and the sources, we have to send the seismic energy away from the fault to the site. And so that's this ground motion prediction equations here. And it turns out that these are the most uncertain of this whole activity, much more uncertain than what we do in geology. So this remains difficult because we have to figure out how to take that seismic energy from the source, propagate it through the Earth's crust, especially through the near surface, to the site. And then there's some kind of curve of probability of exceedance. So how strong the shaking is versus how likely it will be exceeded. And this is a little bit more of a special case of a sort of strong motion seismology, and not so much of geological input there. So here, for example, it is a global seismic hazard mapping program map for Southeast Asia. And so you can see that basically it says 10% exceedance probability in 50 years for peak ground acceleration. So it's kind of a typical way it's presented. And the colors go with the magnitude. So 9.8 means 1 G. So, you know, where it's dark red or brown, you would say, okay, 10% or higher probability of exceeding 1G in the next 50 years. So this is a probabilistic approach. We can't say it's going to happen tomorrow, but it gives a kind of spatial mapping of where expected seismic hazards are and what their variable strength is. So you can see for Indonesia, it's dominated by the subduction zone, but there's a little bit of increased hazard in the area around where we are actually because of some of the upper plate structures. So this is a place where there can be some refinement. You see other parts of the region are much more dangerous actually because of the distributed faulting on land, so Philippines. And then in China, this is kind of anticipating, for example, the Wenchuan earthquake. So that's a kind of a quick example going through the big steps. But now I'm going to go back and I'm going to spend some time showing the kind of modern seismic hazard analysis as it's being done in California. And this may be illustrative for you as you think about, okay, what could we do 10 years, 20 years from now as we sort of have a long-term goal for building an integrated understanding of earthquake hazards. So the two main parts is the earthquake rupture forecast and the earthquake shaking model. So this is kind of like saying the earthquake rupture forecast is 1 and 2, and the earthquake shaking model is mostly 3, and with a little bit of 4. So really the geology and the things that, for example, I know the most about is working with earthquake rupture forecast. So let's talk about that. And so the way you say it in just simple words is, it gives the probability of all possible earthquake ruptures throughout a region and over a specified time span. And that's different than the earthquake shaking model, which says for a given earthquake rupture model, or for a given earthquake rupture, this gives the probability that some intensity measure will be exceeded. And so this is where we see this, distance versus peak ground acceleration, or you can try to compute the wave field itself using a kind of a physics-based approach. So we have empirical attenuation relationships. This is the most common, and then physics-based is the future. But as I said, this gap right here, this distance of the uncertainty in peak ground acceleration as a function of distance is one of our biggest uncertainties in this work. It's actually not, it's more poorly understood than even the geology side of things in terms of active faults. So let's look. So one thing you can do, this is usually not done, but you can go ahead and using high performance computing and a model for how you think the earth works, you can simulate a great earthquake. So this would be one earthquake that occurs on the San Andreas Fault, and we see the ground motions moving away from the rupture. So the rupture is pulsing along the fault surface. It happens for any fault. And so you see then, this uses realistic velocity models for the upper crust. And so these sedimentary basins, like the Los Angeles Basin, is deep. And so the seismic waves reverberate through the basin. Same thing with the deep basins and the south there. So this would be a deterministic seismic hazard assessment for a single event. And so this is where I think things are moving in the future, more physics-based approach, but it's not commonly done for any one place. It's starting to be done for some of California, but it's really essential that we all get in our mind, this is what we're looking at when we see a big earthquake. Very complex ground motions.
The rapid is upper over there. It can also surface rupture on the other locations.
Will there be surface? So it starts here, right there. Okay. So the way this works is that there's a kind of, this is a pulse-based approach. So the part of the fault that's slipping is maybe only about 20 kilometers long. And this pulse moves over the fault surface at about 1 kilometer or 2 per second. And as it's moving over the surface, the slip is accumulating. And so the slip might accumulate in 1 meter per second. So what that means is here, let's say if about 5 meters of slip accumulates, it might take about 5 seconds for this pulse to go past that particular point. And so you see the earthquake come by, see the ground moving, and then you see it heal behind it. So there's no more slippage from this piece of the fault, but the rupture continues to propagate. And so, it's now you see it's moving. The rupture itself is right in here. This is this pulse. This part is already slipped, so we could go there and we'd see 5 meters of offset or 10 meters, but no more slippage, we don't think. Maybe some small after slip. But the seismic waves then, and this is showing velocity. So these colors are meters per second, up to 2 meters per second. So this would, be quite strong to knock people down, buildings down. And so you see it's, this is what you'd call a kind of unilateral rupture. So it just goes along the fault surface from one end to the other and generates seismic waves. And then those seismic waves interact with the heterogeneous volume of the Earth. And so these sedimentary basins really ring. And so we see both amplification, so as well as increased duration of seismic shaking. So this is, like here in Los Angeles, you can see it's still shaking, even though the mountains nearby have stopped because of this complexity of the sedimentary basins, the deep basins. So this is a problem because even though Los Angeles will have a good seismic construction, they have to expect that much longer motion, and especially for maybe the buildings, tall buildings can be a problem. So it shows that an example of how when we study earthquakes, we have to know everything. We have to know how the faults work, but we also need to know the general geological structure, kind of crustal structure to anticipate what's going on. So questions? So you mean the upper end? Nothing happens. So that's the next earthquake. So remember how I was saying about my example of it's like a movie. So this is one earthquake, takes 2 minutes, but then maybe 5 years from now there'll be another earthquake on the next piece. So over 100 years, the whole fault system has earthquakes to allow for the long-term motion to occur. But at any one instant, only a part of the fault breaks. So was this your question? The segmentation? Yeah. So this breaks the southern San Andreas fault sections, but there's more to the north that may break in the future. Questions? Other questions? Comments? Yes. No, this is actual particle motion. So it's just what you and I would do, So not, the seismic weight, the surface wave speed is more kilometers per second. That's what it's moving on the map. Good question. Good comment. Okay, any other comments? I always like this because it's like a picture of an earthquake. No, it's a computer, and it's the strikes that fault, but same thing happens on a subduction interface, same kind of complex behavior, and that's what we're really trying to study. Okay, so here was the outcome of this Uniform California Earthquake Rupture Forecast, which was a community effort. So many people worked on it. It was a large group of scientists and engineers from academia as well as government, from both the federal government, so the U.S. Geological Survey, and the California Geological Survey, and then it was paid for by U.S. Geological Survey and California Earthquake Authority. So this is a group that people, if you live in California, you have to pay a little bit of money, like earthquake insurance. They collect this money. Mostly they just wait till there's an earthquake, and then they're going to have to pay it out. But they use a little bit for research. A little bit, like $1 million, but a little bit to help pay for this work to be done, pay salaries, get stuff done. And so what you can see then is this is like the news. So more than a 99% probability in the next 30 years for magnitude 6.7 of great earthquakes in California. So it's in a way easy to say because it's a big place. It's all of California, and 6.7 is not that great of an earthquake, but it's a plate boundary after all. So this shows it's trying to communicate to the public, okay, guys, we better, be prepared. And so it shows for also, and it's spatially explicit, so we can say, well, if you live in Southern California, this is your probability distribution, different magnitudes, same with San Francisco. So let's just show a little bit of how this was done and where the geology, where the active faults come in. So the main ingredients are kind of the geodesy. So we need to know what the loading is, what the deformation rate is. We need to know where the faults are. We need to know kind of what the historic seismicity is, what have we seen happen there, and then we can compute this rupture forecast. So remember, this is forecast for earthquakes. It's not the ground motion. That would be next. So earthquake rupture forecast. And so the main ingredients, and this is especially where, just a way for us to kind of take apart what we do, is we have fault models. So this is mapping. We need to know where the faults are, where they start, where they stop, what their dip is, how deep they go, because that controls the magnitudes, really. Then we need to know the deformation model. So how fast is the zone deforming? How much then they have to be released by earthquakes? Then the earthquake rate model is, well, how big are the earthquakes? Do we have many, many small ones, a few big ones? How does this work? And then we go into the final sort of probability map of the rupture forecast. And so this work is basically trying to be done in a modular way so that as new understanding is developed, it can be updated. And so that's why this is called USURF 2. They're just finishing USURF 3, so the Uniform California Earthquake Rupture Forecast. They're made the USURF 4. So we can't take pieces just like this, example of these Legos, these toys, where you put one piece in, it works now, but maybe later, okay, we got a better piece. Let's put that in, and we'll constantly improve the pieces. But this modularity helps us to take the problem apart. So first thing is faults. We need to know the faults, geometry in 3D. And so this is California, one view of the faults. And so this would be something that, for example, should be done here. Maybe already is done to some degree, but the uniform 3D database of the faults and their attributes. And so this includes the locations, the dip, and so on. The sense of motion, the rate, the strike slip, dip slip. Okay. Then here's the deformation model. So for each of those faults, we have to say how fast does it slip. So the color here says up to 35 millimeters a year. So the San Andreas fault here in the middle, remember I showed Wallace Creek, that stream channel that was offset? It's right here. So that's, the plate boundary really localized in one place, high rate. Other places, like down here in Southern California, it's more distributed. So we get lower slip rates, but on multiple faults. So Gayatri's fault, for example, this one here, San Jacinto, she worked on this little step over right here, right? So there's main sort of strike slip system as the plate boundary, but then there's many of these secondary dip slip structures that have much lower rates. So they see they're more blue, but they still can be hazardous because maybe they are right underneath some people. So this is a deformation model for fault slip. But we also can use a geodetic deformation model. So, how much are we pulling on the system now? And remember in my little movie, I said that this arrow, it's minus 34 to the east, which means it's moving west, and it's like 32 north. So hypotenuse gives us the length, right? It's about 35 millimeter a year vector. So what's interesting is that the long-term, short-term overall balances 35 or so millimeters per year across the system. But on short term, how we reconcile geologic rates, which are mostly on the fault, and then it's distributed, you see it's pretty smooth, the change in the geodetic model. So this is trying to use all the information we have, but it's over different time scales and take some challenges to be combined. So then the earthquake rate model is basically the probability. So this is like magnitude, frequency, Gutenberg-Richter characteristics. So we'll talk more about those tomorrow. And so we can specify these types of these rates on known faults, but then we have just areas where we suspect there are active faults, but we can't say which one it is. So we just have a kind of an aerial source. That's what these are called. And then there's sometimes somewhere floating around. We can't say for sure, but we can always be surprised. And so this might be a magnitude 6 that could occur anywhere in California, and that's in addition to what happens on the known faults. So this is earthquake rate model, and then the final outcome is the magnitude frequency distribution of the earthquakes. So cumulative rate per year versus the magnitude. And so what they did is they compared also with the historical seismicity. So the model gives an answer that's consistent with what was seen historically. So that's the pluses, and a couple of different ways of calculating things. And so you can see that then this rate model then hands off to the ground motion people. So one final issue with these kinds of models that is being tackled by USERF is aftershocks. So because what I just showed you is kind of a time-independent model. It's every day it's the same probability. It doesn't change with time, but we know if there's an earthquake, a lot of times there's aftershocks around it, and how do we anticipate that? We can use kind of an Omori-type law of decay of the probability of aftershocks with magnitude over time, but maybe we can do better, because in the case, for example, of the Christchurch earthquake, this big earthquake was 7.3 Darfield with surface rupture. Then the aftershocks were here. They were smaller, magnitude 6, right? But they were underneath Christchurch. So this is what was dangerous, was the aftershocks. So this is, ongoing challenge for earthquake forecasting is time dependence. Because we know if there's an earthquake right now, then we have elevated hazard around that area. So that's the end of the first lecture, and this is the topics I covered. So maybe now we can